Our next lesson is going to be on circular motion, and this is part of the unit on circular motion and gravity. So in this lesson on circular motion, we're going to look at circular motion in general, sort of description of what causes it, and then we're going to look at two parts of this: centripetal accelerations and centripetal forces, which will be sort of the very key and the core behind this lesson. And then the last thing we'll look at is we're going to look at centripetal versus centrifugal forces, between the type of force we're going to be talking about here and another one that you commonly hear of, the centrifugal force. So let's move on. Circular motion. So as we discussed earlier in the unit, velocity has both a magnitude and a direction. It's different than speed, which just has magnitude. Velocity has both magnitude and direction. We also know that acceleration is the change in velocity per unit time. We said that it was, the definition of acceleration being the final velocity minus original velocity, all divided by the time. So if there is a change in velocity, we should have an acceleration. But then we talked about, and we said, that if we have an acceleration, we must have a net force, some non-zero net force that's on it to cause an acceleration. So if we have a net force, then we will have a non-zero net force. We will have an acceleration. If we have an acceleration, we have a change in velocity. So therefore, sort of our point 4 here, if you have an object which changes direction but not speed, then it is changing velocity, even though the speed stays the same. And so if it's changing velocity, then it must be accelerating. And if it's accelerating, there has to be a net force on it. This would be the case of, you imagine having someone who's walking around in a circle at a constant speed. And so as they go around the circle, that their speed never changes. Let's say they're going at 10 meters per second, which I guess they're running very fast, very, very fast. That's like Olympic level sprinter speed, but around in a circle. And so they're maintaining the same speed at all points in time. That never changes. But they are changing direction, which means they have to have an acceleration, which means they have to have a net force. And so this would be sort of an example here. The simplest case is the one we described right here. This is called uniform circular motion, when an object moves in a circular path at a constant speed. Okay? When this occurs, the acceleration that the object experiences is called a centripetal acceleration. And the force that results in that centripetal acceleration is called a centripetal force. So let's take a little more look at that centripetal acceleration. The word centripetal, you can break it up into two parts. Centri, which basically is center, and then petal, which means seeking or going towards the center. So it's used because centripetal accelerations always point radially inward towards the center of the curve. So let's take a look at this example that I have over here on the right. We have some car, some automobile, that's this right here. And this automobile is traveling at a speed of 15 meters per second, or a velocity of 15 meters per second. To start with, it's traveling due north. And then after some period of time, it ends up over here on this segment, and now it's not traveling north anymore. Now it's going to be traveling west, and so now it's going in a westerly direction, still at 15 meters per second. So it has not changed its speed, but it has changed its velocity. Now to think about it, in order for this object to change the direction that it goes, it's going to need a force on it. Because, at first it starts off going this direction. To get it so just an instant later it's going to be going in this direction means that we're going to need a force that's going to push it sort of this way in general. Now when we get up here to this next one right up here, is that now we're going to go from here to an instant later where it's this way. We would need a force pointing sort of in this direction. And now down here, you need a force that would point in this direction. Up here, you need a force that would point in this direction in order to get it so it would turn more towards that in the direction it's trying to go here. Now, if you notice something about each of these examples that we've shown here, this one right here would apply right there. This one right here is going to apply right here. This one right here is going to apply right here. This guy that's up here is going to create that force points like this. This force right here points like this. This one right here is going to point right here. This one right here is going to point right here. They all go towards the center of the circle. And this is true for any object that changes direction. If it follows a curve, even if it's just a slight arc, that arc has a radius, and the force that's going to cause the change in direction is going to point towards the center of that arc, towards the center of that circle that's described by that arc. And so it means it's center seeking. If you want a curve, you've got to have a force that points towards the center. Now, if we actually want to figure out the value of that centripetal acceleration, fortunately, it's not too difficult to do. That's the equation that's on your screen, that AC, the acceleration centripetal, is equal to v squared over r. So breaking this down, we have the centripetal acceleration, which is this guy right here. V is going to be the velocity. In this case, really, it's more of a speed because the fact it's squared. That's going to take away any magnitude or direction, or any direction it has to it. And then r is the radius of the curve, us. In the example that we gave here before, the one that's on the left, the radius of the curve we said was 65 meters. That's that value right in here. And so the centripetal acceleration will always be this v squared over r. So, question at the bottom here, what is the centripetal acceleration in this case at right? And so to figure that out, we say, okay, well, we know the centripetal acceleration is going to be equal to v squared over r. So v in this case is 15. So 15 meters per second squared divided by r, the radius, 65 meters. And so if we take that and put that in our calculator, 15 squared should be 225 divided by 65. Get a total of 3.46 meters per second squared, because that would be acceleration. Checking the units on it, v squared would be units of meters squared per second squared divided by meters. That meters is going to cancel out the meters, the squared part of the meter on top, leaving us just with meters per second squared, which is a unit of acceleration, which is what we expect. So that would be an example of how you would find a centripetal acceleration. Now, next question would be, what causes that centripetal acceleration? We already said it's centripetal force, but let's take a look at that and see if that gives us a little more insight into this type of problem. All right. Centripetal forces. The force that causes this acceleration is called a centripetal force because it also points towards the center like the centripetal acceleration, which we sort of know from Newton's second law, that F equals ma, and so whatever direction the acceleration is, the force has to be in the same direction. So whatever force causes the centripetal acceleration, that force would have to be in the same direction as that centripetal acceleration. So let's look at this example, sort of Newton's second law. So we say that Fc, the centripetal force, would be equal to m, the mass, times ac, the centripetal acceleration. Straight up Newton's second. But we know that the centripetal acceleration that we have right here is equal to v squared over r. So the centripetal force would be equal to m times v squared over r. And so this gives us sort of our final equation here, that the centripetal force, Fc, is equal to mv squared over r. This is our definition of a centripetal force in terms of being able to calculate it. Now, this is a way to get it if you know the radius of the curve, you know the velocity of the object that's traveling in the curve, and you know its mass. But there's another way to get your centripetal force. Because remember we said to start with here, in order for the object to curve, it has to have a net force. That net force is the centripetal force. And so a centripetal force is a net force. It is not an additional external force. If I have an object that is traveling around, you know, let's say it's a person that's walking around in a circle like this, is when we talk about what's happening to them at this point right here, is that we said, well, they're traveling in a circle, so they have to have a centripetal force that's going towards the center of the circle. I guess that's supposed to be the center of the circle. We're going towards the center of the circle here, is that you wouldn't say, well, we have gravity pulling them down, and we have the normal force pushing them up, and then we have the centripetal force pushing them towards the center. There has to be something that's causing that centripetal force. And, in this case, it's the friction with the ground. If you're walking, you want to walk in a circle, you've got to sort of push off with your foot. If you're wanting to turn left, you push off with your right foot. And so that means the ground is going to be putting a frictional force against you. If you were on frictionless ice and tried to turn, it wouldn't work. Your foot would slide up from under you and you'd fall straight down because the ground would not be able to apply a frictional force to you and you wouldn't turn. Same thing might be true for an example of a plane. If I'll do a biplane because that's what I feel like doing right now. We have some sort of biplane that wants to make a turn and they want to go in this direction. Well, how do they do it? Well, what they do is that they're going to bank. When they bank like this, they're saying, okay, well, we have a gravitational force, an Fg that pulls down. We're going to have a lift force, which is always perpendicular to the wings like this. And so that's our lift. That should be an L right there. Now, to figure out what the centripetal force is in this case, you would say, all right, well, look at these two forces. Which one of them is going to point towards the center of the circle? Because they're going to be sort of curving off in that direction. Well, taking a look at this, you'd say we can break these up. The Fg has just a y component downward. The lift force, though, has two components, one here and one here. It has an x and a y component. The x component of the lift is this guy right here, points towards the center of the circle. And so for this particular example, where we have a lift force that's pointing in some angled direction, that the x component of that lift is going to be the centripetal force, because that's the part that's going to cause the plane to start turning here. It points towards the center of the path. If you ever have an object that's moving in circular motion and it does turn in some direction, just add up the forces. Figure out which component is pointing towards the center, and that's your centripetal force. And that centripetal force is also equal to mv squared over r. And so that's how we're going to be able to set up to solve problems that deal with circular motion. Remembering that our net force is going to be equal to the centripetal force for objects that are curving, and then we also know that that centripetal force is equal to mv squared over r. Let's try an example. What centripetal force is needed for a 1,200 kilogram truck traveling at 22 meters per second to execute a 45 meter radius turn? Well, two ways to find centripetal force. One is to add up all the forces, find the net force. If it's curving, that is your centripetal force. The second is to use mv squared over r. In this case, we know the mass, we know the speed, or the velocity, we know the radius of the turn. So we're just going to go ahead and set this up just using our traditional mv squared over r. So we say that the centripetal force is mv squared over r. So centripetal force here would be the mass, which is just 1,200 kilograms, times the velocity, 22 meters per second squared, divided by the radius, which is 45 meters. All our units seem to be working out here nicely. And so plugging that in, 1,200 times 22 squared divided by 45. And so we get 12,906.67. Significant figure-wise, everything has 2 here. So this would really just be 13,000. And so we have 13,000, since we have units of meters per second, kilograms and meters, should end up in newtons because we're in our SI base units here. So 13,000 newtons would have to be the centripetal force. So what causes this centripetal force? Well, we said, as a truck turns, it's going to have to be the friction between the tires and the road. So the next question says, what coefficient of static friction is needed to keep the car from sliding in the turn? So let's just think about how this car actually goes about this, or this truck actually goes about this. So they're on the road right here, and then so we have our truck looking from the back. And so for this truck right here, this truck has a gravitational force, Fg, pointing down. It's going to have a normal force that points this way. And so it's also then going to have a frictional force, which is going to point inward like this, so that it will be able to execute a turn going around in that direction. And so that normal force right there is going to have to, did I say normal force? That should be frictional force. Frictional force. That frictional force right there is going to have to be the one that is going to provide the centripetal force. It points towards the center of the circle as opposed to the normal force and gravitational force, which simply cancel each other out to keep the truck from flying off the road or falling through it. So that means that our centripetal force, Fc, would have to be equal to the frictional force in this particular case. Well, we already know what Fc is. It's 13,000 newtons is going to be equal to the frictional force. Frictional force is equal to, in this case, since this truck is not sliding across the road, the mu-s, static friction, times the normal force. And so that's what we have right there. Now, the normal force would be equal, in this case, has to be equal to the gravitational force because, as we said, it's not rising or falling. And gravitational force would be 1,200 times 9.8. So 13,000 would equal to mu-s times the normal force, which is 1,200 kilograms times 9.8 meters per second squared for the gravitation. And so 1,200 times 9.8 is 11,760. So we're going to divide both sides by 11,760 right here. So 13,000. Actually, technically, we should be using the unrounded one, not the 13,000, because, so let's see, that would originally have been, was it 1,200? I forgot what I had originally here. Times 2.2 squared, 22 squared, divided by 45. So 12,906 then divided by 11,760. And so I get 1.0975. So mu-s is 1 point, and so significant figure-wise is still two significant figures. So 1.1 is going to be mu. So this is going to have to be, if the static coefficient, the coefficient of static friction were lower than this, then the frictional force would not be able to apply a 13,000 Newton force, and so this truck would then slide off the road. It would not be able to execute a 45-meter radius turn, 22 meters per second. It just wouldn't be possible. And so this has to be a very, very sticky road. 1.1 is a pretty high value for a static frictional force in order to keep this truck on the road. So let's try another example of applying our centripetal force. If I can get this erased. All right. So next up, what's the maximum speed an 800 kilogram car can take a 50-meter flat curve if the coefficient of static friction is 0.35? So in this case, we have, once again, a car that's going to be going around a curved track here. We know that the curve is 50 meters in radius. We don't know how fast the car is going. We do know that it's 800 kilograms. So looking at it in cross section, here's our car right here. We know it's 800 kilograms is the mass. In terms of the forces on this car, we know there's gravity, Fg downward. We have a normal force, Fn inwards. And in order to make it curve, we're going to have a frictional force, Ff, which points towards the center of the curve to make the car actually go in circular path. So setting this up, we're looking for the maximum speed. That's v. So we're going to have to find v here. And so let's go ahead and set up that our centripetal force is equal to mv squared over r. So m in this case is 800 kilograms. V we don't know. That's what we're looking for here. So v squared we're at a loss on currently. Divided by r, and then we have to do a 50-meter curve. Okay? And so this is our Fc, but we have to figure out what Fc is in order to solve this out. Well, Fc is also going to be equal to the frictional force, Ff. That frictional force is going to have to be equal to mu-s, because the car is not sliding. It says how fast can they go, times the normal force. That normal force should be equal to the gravitational force in this case. So it's equal to mu s times Fg, which is the same as, of course, mu s times acceleration to gravity times the mass. Okay? That's mu s right there. So let's go ahead and set this up, plug it in. So we have 800 v squared over 50 would equal, that's a 50, would equal to mu s, which we're told the static friction is 0.35, times 9.8 acceleration to gravity times the mass, which is 800. Now, a couple things you may sort of notice here. One is that the 800 should cancel right off. So that goes away. The reason why is because this 0.35 times 9.8, 9.8 is an acceleration, 0.35, the static coefficient, is unitless. It has units of acceleration. If we cancel out the mass on the other side, v squared over r, that's your centripetal acceleration, also has units of acceleration. So the mass is actually irrelevant here. So solving this out, we got to get v squared by itself. So we're going to multiply 50 on both sides. So multiply both sides by 50. And so v squared then is going to have to be equal to 0.35 times 9.8 times 50. And so 171.5. Okay, and so take the square root of that. And we get 13.095 for v. And that's going to have units of meters per second because we had everything else in kilograms, meters, and seconds. Significant figures on this, that's 800 kilogram car, just 1 sig fig, 50 meters, 1 sig fig. And so the maximum velocity to the nearest significant figure here is going to be 10 meters per second. And that's as fast as we can take this curve. Any faster and we slide off. Well, road designers know this. And so when they design curves where you have to go you have to have a greater curve for the speed of the road, they bank the curve. And so let's look at what happens if we bank this curve. And let's see what happens this 10 meters per second fastest we could go. So what is the maximum speed an 800 kilogram car can take a 50 meter flat curve? Oops, shouldn't be flat anymore. It's no longer flat. It's banked, so get rid of that flat. A 50 meter curve, if the coefficient of static friction is 0.35 and the curve is banked by 15 degrees. So if we're banked by 15 degrees, then now, here's our angle here. So that's going to be 15 degrees right up there. Our car, which I'm going to turn into a box so I don't have to draw a little bit better here, now has some little different forces on it. Same forces, different directions here. We have a gravitational force that way. Normal force is now angled right here. And the frictional force, which is going to make it curve, because we're curving in this case to the right as we're going to looking at the back of the car if they're going forward. The frictional force, remember, is always parallel to the surface. So the frictional force actually goes down here. Now, taking a look at this, you know, the forces that go towards the center, there are actually two of them now. If we sort of zoom in on this a little bit, we have a frictional force down this way. We have a normal force up this way. Both of these two forces are going to have components that go in the x direction, which is in the centripetal direction. So, you know, our frictional force we could break up into two parts. Our normal force we could break up into two parts. And so the centripetal force then is actually going to be equal to the sum of the x components of the frictional force down here and of the normal force. And so we're going to have to add up those two to find the frictional force, the centripetal force. So we're still looking for that maximum speed. We still know that Fc is equal to mv squared over r, 800 times v squared divided by the radius, which is 50. But this time, this is going to be equal not to just the frictional force, or not just the frictional force, but rather to the x component of the frictional force, ffx, plus the x component of the normal force, Fnx. And so we're going to need to figure out what those are. And so go back to our basic free body diagram here. In this case, if you think about it, this particular car is not rising off of the pavement. It is not falling through the pavement. And so we want to do an axis rotation here to make sure that, that this works. So let's try this out. Just a second here. Okay, it looks like we seem to have lost what we had here, but either way is that what we actually want to look at is actually not rotating the axis on this, but rather making sure that all of our values on our car here, so our component here, our frictional force here, our gravitational force here, it's not going to rise up and down. It's not going to slide up or down the road as it goes through here. And so that means that we sum up these forces, the x direction should sum out to be 0. And so if we look back at what we had here, you know, if we draw out our forces again, we have a right angle right in here, we have a gravitational force here, that we know that we can break down our normal force into an x component here, or a y component that was there. We're going to break our frictional force down, and we're really over-exaggerating our angle here, like this. And so that means that, you know, talking about our angle here is that our 15 degrees should be inside here. It should be inside here. So that means that since this is 15 right here, that our normal force, Fn, that the y component of that should end up being, let's see, that's adjacent, so Fn cosine of 15 is going to have to be our y component, and we're going to from that subtract off the y component of the frictional force, because that y component of the frictional force points downward, and so since that's 15 here, it's opposite here, so minus Ff sine of 15, and then minus as well the gravitational force, Fg, which is going down here, which is simply going to be the mass 800 times the acceleration to gravity 9.8. We know these have to equal 0, and so that's going to be our first equation that we have here. The second one's our centripetal force equation, and so for that one right there is that we know the centripetal force is mv squared over r. 800 is the mass times v squared divided by the radius, which is 50, is going to have to be equal to our y component. So the y component of Fn is simply going to be Fn sine of 15. And then going the same direction is the component of the frictional force. So plus Ff, and in this case it's the adjacent one, so it's going to be cosine. So Ff cosine of 15. So these are our two equations here. Now, looking at this first one, we have Fn and Ff. So Fn is our normal force, and it's related to the frictional force by the coefficient of static friction. And so, you know, really what we can say here is we can say, well, this Ff right here, we really can just replace with mu Fn. Well, we already know what mu is. So mu is 0.35. So actually, we can even go and replace that mu with 0.35. When we do that, then this simplifies this out a little bit. We can actually pull the Fn's out of this first one here, end up with Fn times the quantity of cosine of 15, the term from the first bit here, minus the term for the second one, which is 0.35, the mu sine of 15. Okay. And that's going to end that part right here. Let's move this section right over here, the 800 times 9.8, over to the other side. So 800 times 9.8 ends up being 7840. And so we'll add that to both sides. And so we just get 7840 on this side. This whole long term, we're multiplying the Fn by the cosine 15 minus 0.35 sine 15. This should just have a value to it. And so we can go ahead and calculate that out. So you can say cosine 15 minus 0.35 sine of 15. And so when you do that, I end up with negative 0.987 is what we're getting here. Make sure I do that right. Actually, I think I am in the wrong mode here. Let me switch over to degrees. That might make a difference. So cosine of 15 minus 0.35 sine of 15 in degrees and not radians, 0.8753. And so what we're going to do is we're really going to divide both sides by 0.8753. 0.8753. And so the 7840 divided by 0.87533,91605 ends up being 8956. So the normal force is 8956.52 newtons. All right, well, if we know that, then we should be able to go ahead and plug it in and solve for our velocity here. Because we know 800 times that equals our Fn sine 15 plus Ff, but we already talked about that Ff is just 0.35 Fn. And so writing out the rest of this, we would say, all right, well, 800 v squared over 50, we can actually go ahead and combine that down. 800 divided by 50 is just 16, and so it's 16 v squared, and so we really can go ahead and say, multiply that over, and so we end up with v squared is equal to 16 times the quantity of Fn, 8956.52, times sine of 15 plus 0.35 times Fn, which we said was 8956, 0.52 times cosine of 15, right there. And so that's all times 16 over there. So once again, this is just solvable. So 16 times, open parentheses, 8956.32.52 times sine of 15 in degrees, of course, plus 0.35 times 8956.52 times cosine of 15. So I end up with 41,977. And so we take the square root of that. So 204. So assuming that we've done our math right here, is that unlike our previous one, which we could only go about 10 meters per second, this one can go 204, assuming that once again we haven't made any math errors going on in here. So what you can see is you end up going a lot faster in a case like this whenever the curve is banked than you could if you were traveling at a on an unbanked curve. So let's try one more. This is one that usually gives people a little bit of trouble. One last one before we go on to our last bit on here. And so for this, if it will actually let me do that, PowerPoint. All right, so so a 200-gram rock is swung on a 1.5 meter long sling such that the angle between the sling and the horizontal is 20 degrees. How long does it take the rock to make one rotation? So if we have someone who is basically has a rock attached to a sling, is that as they spin it around their head, is that sometimes you think that's going to travel in basically a straight line circle, but in reality that's not true because the gravity on the rock is going to pull it down somewhat. And so what's going to happen is the rock is going to be out here, and the forces on the rock are going to be gravity pulling it down slightly, Fg, and then there's going to be a tension in the line that's pulling it up. It's not going to end up going straight out like this as it swings around because of the fact that gravity is going to pull it down. And so that's second case doesn't work, so the first case is what we've got here. And so the reason why it's going to stay level as we rotate about our head is because this tension force has components to it. It has a y component this way and x component this way. The y component of the tension has to be equal to the gravitational force. So in this particular case, it says the angle between the sling and the horizontal is 20 degrees. So this angle inside here is going to be 20 degrees right in here. And so given that, we should be able to get a basic idea on what's going on here. So what we know is the gravitational force, Fg, is going to be equal to the y component of the tension, which is just equal to the tension in the line times, let's see, so that's opposite here, so times sine of 20 degrees. So we know that. We also know that the centripetal force, your first thought might be the centripetal force is the tension, but it's actually not, because the center of the circle, it's not rotating sort of diagonally. It's rotating about sort of a circle that has it's going around like this. And so because of that, we're not interested in the tension force as our centripetal force, but we are interested in the x component of the tension. And so that means that Fc, our centripetal force, should be equal just to Tx, which would be equal to T cosine of 20 degrees. All right. Centripetal force, of course, is equal to mv squared over r. M in this case is 200 grams. That's 0.2 kilograms times v, which we don't know, squared, to v squared, over r. It's a 1.5 meter long sling. 1.5 would not be, however, the radius, because the radius is this distance right in here to the center point, not the original length of the sling. That's that distance right here. And so in terms of figuring out what r is, what we know is that there's a relationship here. We know that the angle that's down in here is going to be our 20 degrees. And so this is going to be adjacent to hypotenuse. And so r is our adjacent divided by our hypotenuse, which is the length of the string L, is going to be equal to cosine of 20. And so then r would have to equal to L, that's equals L cosine of 20 right in here. And so that means for our value we put in here, it's going to be L, the length, 1.5, times cosine of 20. That should be a 2, 0 in there. And this is equal to the centripetal force, which is equal to Tx and T cosine 20. Gravitational force, we know, is going to equal to the mass, which is 0.2 times 9.8. So adding all sorts of stuff in here. So trying to simplify this out here, we have 0.2 times 9.8, which is 1.96. So 1.96 is Fg equals T times the sine of 20 degrees. So divide both sides by the sine of 20. So it's going to cancel right here. 1.96 divided by sine of 20 equals out to be 5.73. So T, tension force, is just 5.73 newtons. 73 newtons. Now that we know that, we can use that to solve the rest of this, because we know that we have 0.2, not 0.02, 0.2 times v squared divided by 1.5 cosine of 20 is going to be equal to T cosine of 20. So solving this out for T, we want to divide both sides. Actually, not solving it for T. We already know what T is. Never mind. So let's actually go ahead and plug that in for T. I'm going to re-erase that. So T, we just figured out, is 5.73 newtons. 5.73 times cosine of 20 right here. And so multiplying this out here, so on the right side, 5.73 times cosine of 20. And then we want to multiply that by 1.5 cosine 20 from the bottom on the other side. So times 1.5 times cosine of 20. And then to get that, we got to then divide it by that 0.2 right there to get v squared by itself. And so v squared is 37.94. To find v, we take square root of this. And so take square root of that guy right there. And I get 6.16. So 6.16 meters per second is the speed of the rock going around here. But the question is, how long does it take the rock to make one rotation? And so to figure that out, since we know the speed, we're going to know the distance it goes around in our circle. Well, fortunately, we have a way of figuring out the circumference of the circle, because we know that the radius of the circle is that L cosine 20 right here. And L we said is 1.5. So we just take our 1.5 times the cosine of 20. And that tells us that we have a 1.41, 1.409 technically, but 1.41 meter is our radius right in there. And so just multiply that times 2 pi. So we get a circumference of 8.856. So circumference of 8.856 meters. And since our velocity is 6.16, we say 6.16 is equal to distance, 8.856, divided by the time of one rotation. And so we're going to multiply t on both sides like this, divide both sides by 6.16. And so we should end up getting a time of this divided by 6.16. Of 1.437, so 1.44 seconds. Significant figures, 200 gram rock, just one significant figure here, so time of 1 second rounded, really closer to 1.5 seconds to make one rotation around here. So those are some examples of the types of problems that you would run into whenever you're using centripetal force and centripetal acceleration. There's one little extra thing we want to talk about, just because this throws people off, and that is the difference between a centripetal force and a centrifugal force. Oftentimes you hear these two sort of mixed up, or someone will say centrifugal when they mean centripetal, or vice versa. And so let's look a little bit into the distinction there. So the centripetal force, as we said, it's often confused with what's called a fictitious force, called the centrifugal force. Fictitious does not mean doesn't exist. It just means it's not a force in the same way we've been talking about forces so far. The centrifugal force is the apparent force that pushes away from the center for an object in circular motion. It both starts with center here. Fugal in this case basically means fleeing. And so it's not center seeking like a centripetal force, it's center fleeing, going away from the center right there. Centrifugal or centrifugal forces only appear when the reference frame itself is in circular motion. Think about a case of being in a car going around a curve. When you go around a curve, you feel like there's a force pushing you to the outside of the curve, not to the inside of the curve. We've said before that force, there's a centripetal force which points to the inside of the curve. But this seems to suggest, your common sense says, well, but I'm being pushed to the outside. The reason why is because your frame of reference is in your car. And so your frame of reference is not constant. It's curving. It's moving with the curve. And so that's when you're going to end up with a centrifugal force. Sometimes it can be a centrifugal is another way of pronouncing it here, and that makes it even more confusing. Centrifugal with centrifugal. So I'll try to say centrifugal whenever I can. The centrifugal force is called a fictitious force because it's not caused by an interaction with another object, but rather it's a consequence of this reference frame taking a curved path. All the forces we've discussed so far have basically been forces between bodies. Either contact forces like the normal force or a frictional force, or some force that's transmitted over space like the gravitational force, or forces, we haven't talked about them, but forces of between like electrical charges or magnetic fields that can cause forces. These are all forces between bodies. The centrifugal force isn't caused by interaction with another object. It's simply a consequence of taking that curved path. If you want to think about what actually sort of causes it in a physical sense, It's basically caused by the inertia of the object. You know, if you're going in a car and the car turns, you know, your inertia wants to carry you straight forward in a line here. Remember, this is Newton's first law, that object in motion wants to remain in motion at a constant velocity, not a curving velocity, at a constant velocity, unless an outside force acts on it. And that's your centripetal force is the outside force here. But because your inertia wants to carry you forward and your car wants to curve to the side, is that you feel like you're being pulled to the outside because you're actually trying to travel in a straight line. And it's only the car that pushes inward that makes you feel like you're being pushed to the outside. You know, you're not actually being pulled to the outside in that curve. It's just the car is being pulled to the inside by the centripetal force. And so it's basically your reference frame, the car curves while you try to keep going straight. And that gives you this impression of a force. And so this is our fictitious force. Now, if you want to do physics in a rotating reference frame or curving reference frame, you are free to do that. The math will all work out. The problem is that you have to add this centrifugal force term into your calculations, which make things more complex. And so because of that, it's usually easiest to try to do your math in a reference frame that is not curving, it's not rotating, or it's sort of set. And that's what's called an inertial reference frame. And so an inertial reference frame is one that where the reference frame is not curving, it's not rotating, and the reference frame itself is not undergoing an acceleration of any kind. It might be moving at a constant velocity, that's perfectly fine, but it's not accelerating. And so we try to pick non-accelerating reference frames whenever we can. That way we don't have to worry about things like these centrifugal forces. So as long as we have an inertial reference frame, and everything we've done so far this year we can ignore the centrifugal force. And so that's what I would suggest. If you ever have a problem where you're trying to figure out what's happening with someone who's in a car, don't do it from the car's reference frame. If you're in a plane that's banking, or you're on the silly silo, or you know, if you've ever done the thing where you get onto a merry-go-round, spin up really fast, and try to throw something to someone on the other side, it ends up the ball looks like it curves all of a sudden. That's an example of a type of fictitious force that's a consequence of the centrifugal force. Another one would be, for example, the Coriolis force, which is the one that's responsible for the wind patterns on Earth, or responsible for the fact that we have to if you fire a missile from a spot north to a spot south on the Earth, is that because the rotation rates are different, you know, depending, well, the rotation rate in terms of number of radians per second is the same, but you know, if you're closer to the equator, is the faster you're moving because the radius of the circle around the Earth is larger. And so the fact that the Earth is rotating while you fire a missile from a northern point to a southern point causes the missile to curve off into a non-straight path. And that's an example of a fictitious force here. And so there are cases where you do have to deal with a curved reference, moving, rotating, or curving reference frame. But for this class, we're going to stick with inertial reference frames. We'll keep things a lot easier.